Okay, so now this first derivative test is actually used to identify extrema of function, actually relative extrema. So basically, if the function is continuous on an interval from a to b, in which c is the only critical number, if f is differentiable on the interval except possibly at c, then f of c can be classified as a relative minimum, relative max, or neither, as shown below. So basically, number one says if the derivative is negative to the left of the critical number and positive to the right of the critical number, then f of the critical number is a relative min. So basically what we're saying here is, notice down here, if you look at this, this is obviously a relative minimum point. If you look to the left of the number, you can see the function is decreasing, so that therefore the derivative must be negative. But then just to the right, the function is increasing, therefore the derivative is positive. So if the derivative is negative to the left, therefore it's decreasing, and positive to the right of a critical number increasing, then we must get a relative minimum in that case. So in that case, we get a relative minimum. Now, if the derivative is positive to the left of the critical number and negative to the right of the critical number, then we get a relative max. So you can see here, this is obviously a relative max point on this graph. And notice that as you, to the left of the point, notice that the function is increasing, therefore the derivative must be positive. And then just to the right, the function is increasing, so the derivative must be negative. So to the left of that critical number, the derivative is positive. To the right of that critical number is negative. So therefore, we must get a relative max at that point. And now, a couple of other things could happen. If the derivative is negative on both sides of the critical number, like right here, this is a critical number because the vertical line goes tangent here. But if you look to the left of the critical number, the derivative is negative, and I can tell that because it's decreasing. And then just to the right of the critical number, it's negative. So therefore, it never turned around. It just continued to decrease. So you don't get an extrema there. So you don't get an extrema there. And then if it's positive on both sides, then you don't get an extreme value either. Here is a critical number because the derivative is 0 here, but if you look to the left, the derivative is positive since the function is increasing, and to the right, the derivative is positive. And so if both sides of your critical number, if on both sides of your critical number the derivative has the same sign, like here or here, then you're not going to get an extreme value in those cases. You're only going to get an extreme value if you have the derivative negative to the left of the critical number and positive to the right, or if the derivative is positive to the left and negative to the right. That's when you're going to get extreme values. So we can now use that information to answer some questions. So let's go back to some that we've already worked with. Now, we took this function earlier and we found that it has a critical number at -2. And we found that if we tested a number to the left of -2, the derivative was negative, and if we tested a number to the right of -2, the derivative is positive. So since the derivative is negative to the left of the critical number and the derivative is positive to the right of the critical number, then based on the first derivative test, we must get a relative minimum at the critical number, and that relative minimum is whatever the y value is at the critical number. In this case, it's 0. Now, on this one, the only critical number that we had here was x equals 0, and well, we did have the endpoints -2 and 2, but let's just focus on 0. Notice when I tested -1, the derivative was positive, and when I tested +1, the derivative was negative. So to the left of 0, the derivative is negative. To the right of 0, the derivative is positive. I'm sorry, I said that backwards. To the left of 0, the derivative is positive, and to the right of 0, the derivative is negative. And so, therefore, based on the first derivative test, we must be getting a relative max of f of 0. Whatever f of 0 is must be a relative max. Now you could also consider f of negative 2 and f of 2 as relative minimum, because remember this is actually a semicircle that looks something like this, and so at these two endpoints this is the lowest value in its neighborhood, this is the lowest value in its neighborhood, so technically those points are actually relative minimum, because the graph doesn't go anywhere to the right or anywhere to the left of this point. So anyway, but I'm really just focusing on the critical numbers that are within the intervals. Now this function, we found that the critical numbers were 0 and 4, and let's consider 0. To the left of 0 the derivative is positive, to the right of 0 the derivative is negative. So based on that, we're going to get a relative maximum at 0. And you can see, here's the picture, and you can see at 0 we definitely get a relative maximum. The derivative is positive to the left, negative to the right. And now at the other critical number 4, well, to the left of 4 the derivative is negative, just to the right of 4 the derivative is positive. So therefore we're going to get a relative minimum at 4, and you can see there's the relative minimum point right there. And actually the relative minimum is the y value, negative 96. Okay, here's another function here. We found on this function, we found that you had critical numbers of negative 2/3 and negative 1. Okay, negative 2/3. Let's focus on negative 2/3. A number, when I picked a number to the left of negative 2/3, the derivative was negative, and when I picked a number to the right of negative 2/3, the derivative was positive. So based on what the first derivative test says, then f of negative 2/3 is actually a relative minimum, because it's, if you look at here, here's the point, and you can see the derivative is negative to the left and positive to the right, so you get a relative minimum there. And then here, once again, the domain actually starts at negative 1, and this point could actually be considered to be a relative maximum, since there's no other values are in this neighborhood that's higher than this point. Okay, let's take a look at this one. When I got the derivative and found the critical numbers, I found the critical numbers were 1 and negative 1, and so let's focus on negative 1. To the left of negative 1 the derivative was negative, to the right of negative 1 the derivative was positive, so at negative 1 I'm going to get a relative minimum of negative 1/2, and you can see it's right there. Okay, and then at positive 1, to the left, just to the left of positive 1 the derivative is positive, just to the right of positive 1 the derivative is negative, so that means I'm going to get a relative maximum at 1 of 1/2, and there's the relative maximum right there. Okay, this one is very similar to the other one, so I don't want to spend a lot of time on it, but the critical numbers were at 0 and 1, and so to the left of 0 the derivative was positive, to the right of 0 the derivative was negative, so at 0 I get a relative maximum, and then at 1, just to the left of 1 the derivative is negative, just to the right of 1 the derivative is positive, so at 1 I get a relative minimum. Okay, now this one, remember I had critical numbers at 0 and also at plus or minus 2. Well, let's look at negative 2. Just to the left of negative 2 the derivative is negative, just to the right of negative 2 the derivative is positive, so that tells me by the first derivative test that the point negative 2 and its y value, which actually is 0, the point negative 2, 0, which is right here, is actually a relative minimum. And then at 0, just to the left of 0 the derivative is positive, and just to the right of 0 the derivative is negative, so the critical number 0 gives me a relative maximum. And actually it says here that's 2.52, but if you plug 0 back into this function you actually get the cube root of negative 4 squared, or the cube root of 16, which reduces to 2 times the cube root of 2. So that's the exact value of the y value. But anyway, that's a relative max. And then at 2, to the left of 2, the derivative is negative. To the right of 2, the derivative is positive. So at the point 2, 0, you actually get a relative minimum. And again, I'm getting the y values for negative 2 and 2 by just plugging them into the function up here. And that's how I'm getting the y values. So that's an example of that. Now, there's a trig example. This trig example I did a while ago, I'm just going to go ahead and show you here that, let's see, I don't know if I listed this. Probably didn't give you the, looks like I didn't give you the results, but let me show you the results here. Okay, so let's go back to this function now. So at pi over 2 we had a critical number, and remember when I checked to the left of pi over 2 the derivative was positive, but just to the right of pi over 2 the derivative was negative. So that tells me that f of pi over 2 is a relative max. And then at 7 pi over 6, to the left of 7 pi over 6 the derivative is negative, to the right of 7 pi over 6 the derivative is positive. So that tells me I got a relative min. And actually you can see this. Here's f of pi over 2, there's your relative max, and here's f of 7 pi over 6, there's your relative min. And then at 3 pi over 2, to the left of 3 pi over 2, I got the derivative was positive. To the right of 3 pi over 2, the derivative was negative. So I get a relative max here at 3 pi over 2. And then for 11 pi over 6, to the left of 11 pi over 6, the derivative is negative. To the right of 3 pi over 6, the derivative was positive. So at f of 11 pi over 6, I get a relative min. Now I didn't give you the y values here. You'd actually have to plug these x values into this function up here to get the actual y values. So I'll just leave you to do that. But that's basically the first derivative test to identify whether you get relative minimum or relative maximum at these 4 critical numbers. So that's the first derivative test. There's another derivative test we'll talk about later that actually uses the second derivative to identify extrema. Now, here's a few practice problems if you want to practice on these. And you can, over here I gave you the answers to each one. So you can apply the first derivative test to these and see if you can find the relative minimum and the relative maximum. Now remember, the relative minimum and relative maximum are the y values, not the x values. So they occur at the particular x values, but the actual values are the y values, or the f of x values. So that pretty much covers relative extrema. And in the next chapter, I'm going to talk about something that shows, if you'll notice, this graph here, as you go up here, it has sort of a downward curve, but somewhere in here it switches from a downward bend to more of an upward bend. And so that point is actually called a point of inflection, and this is called concave down, and this portion of the graph is concave up. So in the next section we're going to learn about concavity and points of inflection. See you later.